talking on short transmission line. We were talking on transmission line protection using overcurrent and earth fault relays. Then we carried out certain experiments which are feasible in the laboratory environment so that the laboratory can design them. Now we have few 3, 4 or 5 more experiments which are not on power system protection but which are on power systems in general. These are very simple experiments. You may find that why these simple experiments are done, but these simple experiments are giving many new features, many new learning outcome. So we have prepared this. This laboratory in Vallabh at Birla Vishwakarma Mahavidyalaya, Gujarat, India, has been praised by all states in India, and it has been rather praised abroad also. So we are going to talk on short transmission line now, friends. Actually, in power system protection laboratory itself, very few experiments are there. And in power system also, people do not find many experiments. Most of them are study experiments. So when you come to laboratory, it should be something to be done. Some readings have to be taken, some observations have to be done, some graphs have to be plotted, some conclusions have to be made. So all these things are very obvious in laboratory. In theory, we are studying everything that has to be confirmed in experiments. And I very much like experiments. I very much like laboratory. The day I joined BVM, principal told me that you are a hard electrical engineer and we have received grant of rupees 16 lakhs from AICTE recently, and you build up a very good power system protection laboratory. And right from 1986 I started. Probably in 1990 it was completed. It took about 4 years because the laboratory was not done commercially. No orders were given, no tenders were floated. We had wired the laboratory ourselves. We had given the projects to the students, and using the knowledge of the students, using the efforts of the students, we have been successful in wiring this laboratory. So this experiment is a fruit of that uh, experiment, that trial that we had done. Uh, actually, you will find that the transmission lines in power system are 66 kV, 132 kV, 220 kV, etc. So one would worry as to how 66 kV can be simulated in laboratory. But no, we are not simulating on 66 kV. We are simulating on simple 230 volt. But the readings that we obtained are exactly same as what we get in short transmission line, right? So this is possible. This is not impossible. What we have done to give a feel of the transmission line, what we have done is we have not rather uh, we have not uh, used emitters. We have used kilometers. That means we have not done anything. We just wrote K before A. Actually, we asked from the market the meter, as I want a meter 0 to 1 ampere, but which should be capable to read kiloamperes, so that it has to be connected with PT and CT. So CT PT operated meters we wanted. We did not connect CT PT. We just used kiloampere words, so that it would give you a feel that some 100 ampere, some 200 ampere is passing through the transmission line. Similarly, kV, not 220 volt, but we write 220 kV, not 66 volt, but we wrote 66 kV. And in watt also, we did not write watt, we wrote megawatts, because kV into kW, sorry, kV into kiloampere would give you megawatts. Therefore, we wrote megawatts, and meters were also reading accordingly. So this is how the experiment was carried out. Uh, what was the motivation of the experiment? Why should we do experiment? You see, whenever we do any experiment, we should have some motivation. We should have some feeling, some desire, that why do we want to do this experiment? What learning outcome we will get? Will it be useful? So our motivation was, it is essential to find out the efficiency and regulation of transmission line. If the efficiency of transmission line is 80%, it's of no use. You see, efficiency of transmission line is very good, and it has to be very good. And if it is not turning out to be good, then there is something wrong. We have to change the parameters. The regulation also should be good. So this has to be tried, and the line has to be so designed. And if these parameters do not fall within allowable limits, the design must be changed to bring them within limits. So actually speaking, you have to design a short transmission line before really erecting them. You do not have any component in your hand, and you are designing. And then when you find that the design is okay, then you erect the component, then you commission the transmission line, and then you will see that the results are as same as what you thought. So this has to be done, and therefore I am telling that this exercise is very important, very motivating exercise. This is not a simple exercise that we are doing in theories. You see, in theory we read short transmission line, medium transmission line, we get marks also. But finally, what we learn when we go to field, when we go to the actual practice, if somebody asks, what is this, what is that, then we are fumbling. We are not being able to reply, because we do not have a full knowledge of that. We have not studied the theory well. We have not done the experiments according to what we should do. So what I have done, what I have tried is to design the experiment in such a way that in the field practice you do not fail. So after motivation, the uh, objective, what is the objective of the experiment? Objective of the experiment is to find out the efficiency and regulation of a short transmission line. And we also will find out the generalized constants of short transmission line, right? That is also very important, because what are the constants? People, while they are analyzing, they are analyzing in terms of certain constants, right? For any four terminal network, so to say, it is not for transmission line. For any four terminal network means there is a network into two inputs are there, two outputs are there. These are four terminals. Generalized constants are there. So we have to find out the generalized constants. Uh, The whole experiment has been simulated in single phase version. We did not want to make it complicated. So to understand, we made it in single phase version. We have used rheostats to simulate the resistance. Uh, for example, 5 ohms, 2 amperes. 2 ampere is a small scale. In transmission line, there is not 2 ampere. We will be writing 2 kilo ampere, right? But 5 ohms is quite, uh, so to say, it is quite natural. 5 ohms is the typical resistance of a transmission line. So 5 ohms is a typical resistance. That's what we have used. What we have used is not non-typical. Hmm. Just like that is not selected. Similarly, reactance, if you talk, I have a reactance which is variable 0 to 20 ohms, and I have taken taps out 5 ohm step, 10, uh, 10 ohm step, 15 ohm step, and 20 ohm step. That has been taken out of the reactor, so that we have got reactors with us. So we have a reactor to simulate the line reactor, because line has resistance and reactance, and therefore we should have resistance and reactance. Reactance was of 1 ampere capacity, because in market we got 1 ampere. Actually, we are not going to pass more than 1 ampere in any case. For rheostat, what we have done, we have used 1200 ohms rheostat, but we have used 5 1200 ohm rheostat, so that totally 1200 divided by 5 would give me some 220 ohms, if I think so, right? 1200 divided by 5. Uh, but do thus means 220 panchokuvis means, sorry, 240 ohms it would give me total resistance if I make all the switches on. But I can control the load. I can make the load on or off, because on short transmission line load is not predictive. More or less load will be there. So you have to take readings on all different loads. Ampere capacity was 0.6 amperes. But to see the effect of power factor of load, we have connected one 250 ohm reactor also in series with the load bank, resistive load bank, right? 250 ohm reactor. Once again, it has also 5 taps, 50, 100, 120, 150, 200, like that. So there also you can vary the value of the rheostat if at all you want to, right? As I told to you, ammeters, voltmeters, wattmeters are used, but they are marked as kiloamperes, kilovoltmeters, and megawatt meter, so that you can have a feel as if you are working in real transmission line. Uh, Transmission line, as you know, has 4 parameters. One is series resistance, series inductance. Then we have got shunt capacitance, because any transmission line has a capacitance with reference to earth, and shunt conductance. Conductance is the resistance of the insulator, DC resistance of the insulator. It is very large. It is some 200 megohms or 300 megohms or 500 megohms, right? So it is very large. Therefore, the current flowing is very small. It's a leakage current, right? But that conductance is there. So in your line also, these things should be there. For a line of length equal to or less than 50 kilometer, effect of shunt capacitance and shunt conductance is so low that this can be ignored. So what we are doing for analysis, we have to do something. So while analyzing, we are dividing the transmission line in 3 parts. Short transmission line less than 50 kilometer. Medium transmission line more than 50 kilometer. and long transmission line which is 200 kilometer, 500 kilometer and 1000 kilometer like that. For long transmission line, you will not be able to imagine or rather assume resistance as lumped. You will have to assume them per kilometer, right? So every kilometer there will be resistance, every kilometer there will be inductance, every kilometer there will be capacitance, every kilometer there will be conductance. And the analysis becomes little complicated, little difficult, and that has been done in the books. However, for power system one level, we have not thought it proper to go for this complicated analysis. This is one thing. Another thing was that also, that to bring in so many resistances, so many capacitances would be difficult in a laboratory. Therefore also the experiment of long transmission line is not done. Uh, the equivalent circuit can be drawn for transmission line as shown in figure 1.1 in the next slide. Uh, hmm. Transmission line is shown in figure 1.2 and figure 1.3 shows the vector diagram of transmission line. So in the next slide, you will be seeing this. This is your transmission line in general. Hmm? This is the general transmission line. Say long transmission line. Resistance R per kilometer, inductance, inductive reactance X per kilometer, C capacitance per kilometer, G conductance per kilometer. So it is like that. You will send the voltage Vs, but you will receive the voltage Vr which is less than Vs because voltage will drop in all this process, resistance and reactance, etc. Right. So, but Is and Ir are there. They will also be changing. They will also not remain same because you see there will be some current fed from the capacitance, right? Capacitance will feed reactive current. Therefore, there will be change in this. So these are the, so R is the resistance in ohms per kilometer, X is reactance in ohms per kilometer, like that, C and G. G is the conductance. If I go next, if I come to short transmission line, it becomes so simple because there is no capacitance and no inductance. Therefore, Vs is the sending end voltage, Vr is the receiving end voltage, I is the current because same current is passing. There is no current in capacitor. R is the resistance, total resistance, X is the total inductance, and there is a load, right? So short transmission line becomes, this simple. The circuitry of short transmission line becomes simple and we have to analyze this circuit. If we go further, the vector diagram is like this. If I take I current as the reference, then the voltage VR, receiving end voltage, is at an angle phi r. That is the receiving end power factor is less. It is only the power factor of load, right? So it is a receiving end power factor. But as you go toward sending end, the power factor of inductance of line is also added. So power factor, the angle at power factor will worsen. Power factor will be bad. The angle will increase. Therefore, phi s, the sending end power factor is more. To VR, I have to add IR, current into resistance. Right? So that voltage I have to add. And IX, which is at 90 degree. So I get IZ, that is the total inductive voltage drop. Right? And then finally I get Vs. So this is the simple vector diagram. I mean, there is nothing difficult. As I told you, this experiment is very simple. Uh, for third year or fourth year student, this would be very simple. But when students appear in first year and second year, they find it little difficult to understand because many concepts are not clear. And second thing that I have observed in 2011 was my last year. 2012 I retired, so I was not given any load. 2011 June, the new batch came. To that, I was given basic electrical engineering. It was a task for me. It was a challenge for me. There were about 60. Our strength was 60 students in that class. Out of 60 students, some 48 students did not want to go to electrical. They wanted to go to computer and IT because they are the good branches according to people, according to parents, according to students. Therefore, it was a task for me to make them take interest in electrical. For one complete year, I did so much of labor and I made so much of effort that all 48 students started believing that we can earn from electrical. Electrical is a good branch and many things can be done. Actually, now you see branches are not electrical, mechanical, civil. We are naming, but branches have become interdisciplinary. In our electrical branch, there were about 22 computer subjects out of 40. 22 were computer subjects. No doubt in that. Say computer application power system, that is also there. Hmm? Computer uh, computer aided design of machines, that was also an experiment. So experiments are like that, and we have not to use the basic computer. We have to use the knowledge of computer. We have not to use direct computer. We have to use the fruit of computer, right? We have to use the application of computer. But then we need the knowledge of computer. So now the subjects are interdisciplinary. The disciplines are interdisciplinary, and therefore there is nothing like electrical, there is nothing like mechanical, there is nothing like metallurgy. There is nothing like, so to say, uh, the telecommunication or communication and uh, electronics. So branches are merged together, right? So you have to think like that and then start taking interest. And if you start taking interest, you will feel that the experiments are very good. The knowledge is very good and you must gain that knowledge. This is a 4-terminal network, figure 1.4. I've got a passive network. Network is passive. It is not active. It does not generate current. It does not generate voltage. It's a network. I am giving voltage Vs to that, sending end voltage. Current Is to that, right? Current IR is coming out of the network and voltage VR is coming out of the network to which I connect the load. So when I do this, I have to analyze this 4-terminal network and to find out the things, to find out the constants of these things and to make the meaning of these constants, right? So this is a short transmission line. Going further, the experimental setup is like this. You see this 230 volt 50 hertz single phase auto transformer is everywhere available. 230 volt input, 0 to 250 volt output. That is, or 0 to 270 volt output. It is mostly available in all laboratories. 4 ampere is enough because we are not going to pass even 1 ampere through this. because our total load is not that bad. So we are not going to pass very large current through this. So 4 ampere auto transformer is enough, right? Then I have got, we had prepared the complete specification also. You see, it would be difficult rather to it would be difficult rather to explain everything, every specification, etc. Time is a constraint, therefore I cannot explain. But I had prepared the list of components, BOQ जिसको बोलते हैं, bill of quotations, and the specification of each equipment so that you can purchase it from the market, right? And also I had given in my experiment now, because it might have become obsolete, because I had prepared laboratory somewhere in the year 1986. Those uh, uh, people who are selling the item may not be selling, they may be selling something else. Market is changing day by day. So at that time, whatever selling was there, say who is selling auto transformer, I had given about 8 vendors of auto transformer, 8 vendors of emitter, 8 vendors of voltmeter, 8 vendors of rheostat, etc. So that one can easily write letters to them, prepare specifications were also readily prepared. People can float specifications and can do the experiment. I mean, the exercise was done to the fullest so that the teachers should not find it difficult to uh, design the experiment like that. Then through variable terminal, I have got emitter, because I can have to rather 66 kV, 132 kV, 220 kV, any voltage I want to adjust, I can adjust. You see, it is 66 volts only, not 66 kV. But I am telling kV because I have written in the meter kV. Therefore, 66 kV, 132 kV, standard voltages I can adjust. Current I have to measure. I have got watt meter, right? And then I have got resistance transmission line parameter R and L. Then the receiving end wattmeter, receiving end voltmeter. Right, current is the same because it is a series current, so there are no two currents. I've got 5 resistance for resistance bank, 1200 ohms, 0.6 ampere, and uh, load reactance to show the effect of power factor. What is the effect of power factor on uh, the performance of the line? What is the effect of power factor on efficiency of the line? What is the effect of power factor on regulation of the line? That I have to analyze, you see. So these things are very important, and because these things are important, because then only you will be able to tell to the consumers that if you keep power factor low, then you are at loss, because our efficiency is getting worsened, and because our efficiency is getting worsened, we'll ask you from you more money. आप अगर पावर फैक्टर बिगाड़ोगे तो हम आपके पास से ज्यादा पैसे मांगेंगे. We will ask for more money. If you improve your power factor, then we will give you rebate. You see, some such thing can be given, because only when these things are given, if you give to the kids a chocolate, they will do any work that you want to fetch out from them. You have to give them chocolate. You have to give them lalach. You have to give them something. Similarly, electricity boards also doing is like that. You see, less power factor, more money. More power factor, less money. You have to pay less bill, right? That is what is to be done. So these, so many things are to be done in short transmission line. A very simple experiment of short transmission line has been extended to such a limit that one can understand what a transmission line is, right? Then if you go further, what we want to measure, we want to measure efficiency of the line, we want to measure regulation, we want to measure line losses, I square R losses. we want to see the effect of power factor of load on efficiency and regulation, and we want to calculate generalized line constant. This is all what we want to do. Yes, so what are the formula? Vs is equal to Vr plus Iz, very obviously. Vr plus Iz, that is the drop. That gives me Vs. Ws is equal to Vs I. I is the same, cos phi s. Right. Wr is equal to Vr I cos phi r. Ws minus Wr is equal to I square r losses. That is line losses. Efficiency is Wr divided by Ws into 100. Wr will always be less than Ws because some losses have gone. I square r losses have gone. And you see, for those I square r losses, nobody is paying. What is being paid? Your meter rotates, that you are paying. Your meter is reading something that is being paid because you have to ask for payment on the basis of what you are consuming. But what is consumed by the line, what is consumed by I square R losses, what is consumed by the so to say the iron loss and copper loss of transformer, what is consumed by iron loss and copper loss of generator, that is not paid by people, right? So you will have to bring these figures to as low as possible. Efficiency is this. Regulation is VR dash minus VR upon VR into 100. What is VR dash? VR dash is receiving end voltage at no load. At no load, what is the receiving end voltage? Minus VR. VR is when you go on loading, the voltage will be less. So that gives me the regulation. The regulation should be as low as possible and efficiency should be as high as possible. Right. Now, for terminal network, this is the general equation. Vs is equal to AVR plus BIR and Is is equal to CVR plus DIR. A, B, C, D are generalized constants. Obviously, B is in ohms because B is B upon I, that is B. B will be in ohms. C will be in mhos because I upon V. So C will be in mhos. A and D. A is Vs upon Vr. So it is dimensionless. Similarly, D is dimensionless. And another important thing that comes out of this is, for any four-terminal network, AD minus BC is always equal to 1. If you find AD minus BC, it is always equal to 1. So these constants can be practically determined, and you can verify this whether AD minus BC is 1 or not, and all these things you can verify. And for doing this, for finding out generalized voltage, generalized constant, what you will have to do? You will have to do OC and SC test. You do open circuit test. Open circuit test means current is 0. IR is 0. IR is 0 means BIR is gone. So you will get Vs is equal to a VR. So Vs minus VR, whatever is there, is A. Right? Similarly, you can go for short circuit test. Short circuit test means that IR is 0. Short circuit test means IR will not be there. IR is 0. You are short circuiting. You are short. So you are short. Sorry. Vs upon VR. Vs upon VR means when IR is 0, you are not passing any current. That is open circuit test. And short circuit test means VR equal to 0, not IR equal to 0. I'm sorry. VR equal to 0. VR equal to 0 means you have to short circuit the secondary terminals. So IR will be very high. And because IR will be very high, Vs will be very high. Therefore, while doing short circuit test, you will have to be very careful that you will have to reduce the voltage. You will have to reduce the voltage. Voltage should be in your power, right? So like that, ABCD constants can be measured, and this AD minus BC is equal to 1 can be confirmed. That is the short circuit test. So now what is the procedure? How you will do the experiment? Connect the sending end terminals to L and N of transmission line, because we had wired most of the things permanent, so that student has to wire less. Our main purpose was that the student should understand what is the effect of these different things. Because you see, in wiring it takes so much long time that the student gets less time in understanding. So what we did in most of the laboratories at BVM, that we wired ourselves. We kept the uh, the experiments readily wired. No doubt, where the wiring was required, where the wiring was meaningful, so many wires we kept open so that we can ask the student to wire also, because there are certain wiring which are important. So connect the sending end terminal L and N to the transmission line through the auto transformer. Then short X and L, right? Short load reactance. Because we do not want to see first the effect of reactance. First we will see only resistance. So X and L, I will show you what is X and L. What is X and L? Please see. X and L. X and L is shorted, means load reactance has gone. We want to see the effect without load reactance, and then we will see the effect with load reactance, right? So short X and L. Then switch on the supply. Take care that the auto transformer was at 0 voltage. Yes, before switching on, you have to see that auto transformer is 0 voltage. Otherwise, very large voltage will pass through the line and something may get burnt. So auto transformer must be at 0 voltage. Slowly you increase the auto transformer to 66 kV. Not kV, 66 volts as such, right? But it is kV. So take no load reading. You have to take no load reading, because you have to make ABCD constant. So you will have to make IR equal to 0. So take no load reading. Then load the line and take different readings and tabulate them. Go on loading the line. You have got 5 resistances. Make resistance 1 on, 2 on, 3 on, 4 on, 5 on, and tabulate them. Compute cos phi s, Vs, Ws cos phi r from calculated value of Ws, efficiency and regulation. Draw vector diagram to scale and confirm the observed values. That is what you have to do. So now what tabulation you have to make? Note from table 1.1 that line losses increases with increase in load. You have to see this from table 1.1. Table 1.1. What I am doing? VR in kV, Vs in kV. When I is increased, obviously difference between Vs and VR will be more, and therefore regulation will be deteriorating. Regulation will be deteriorating. And also, as I is more, I square R losses will be more, so efficiency will also deteriorate. So this is what you have to observe, right? And for observing, we'll be doing 2 readings, Vs kV observed and Vs kV calculated also. Calculated means Vs is equal to VR plus Iz. That you can always do. So calculate them and compare them whether they are more or less equal or not. Similarly, Ws megawatt and Ws megawatt calculated. Megawatt observed means whatever watt meter reads, and what is calculated? WR, whatever you are reading, plus line losses. Line losses is I square R. R you know, because R you have connected, right? So that you can do. Then you measure cos phi r, right? Cos phi r is there because phi r is available. right? Phi r is available. Therefore, cos phi r you can calculate because angle between V and I is there. Or other way around, WR is equal to VR I into cos phi r, and WR divided by VR upon IR will give you cos phi r. So cos phi r you can calculate. Similarly, cos phi s you can calculate. Efficiency observed. Efficiency observed is WR upon WS is observed. But you can calculate also. Efficiency you can calculate also. WR plus I square R losses. Did you get WS or not? That you can calculate. Regulation observed. VR dash minus VR. That means no load reading VR minus load reading VR. That calculate observation you can do. But you can calculate also, right? Because you know the formula for calculation. So using all these things you can do this. So this is what you do. So find out constant B and D experimentally respectively, and uh, receiving end and terminals are to be shorted. So in one case terminals are to be open circuited, in another case terminals are to be shorted, right? When you are measuring A, B should not be there. B should not be there means B will be there. B is a constant, but IR you can short. IR will IR will not be there. IR will not be there means current will not be there. So open circuit. So it's an open circuit test. When short circuit test, VR should be 0. VR should be 0. A cannot be 0. VR is 0 means short circuit the receiving and terminals. So that's what you have to do for short circuit test. So short circuit test and the open circuit test you have to do, and you have to measure different things, right? So measured value and calculated value are correct or not, that also you can rather see. Another thing is this what we have seen. Generalized constant, as I told you, by shorting and opening, you can find out constants, and the constant that you have measured is this, right? And you can practically you've done, but theoretically also you can find out the constants, right? So because theoretically you are not V, you know Vs, you know Vr, theoretically you know everything. So use theoretical values for theoretical constant and use practical values for practical constant. So this is what you can do. So this is what you've done. Then there are questions. So answer to the questions I am not giving. You have to you have to give the answer to the question. What is the effect of power factor on load? So you see, once you had short circuited that reactor, then keep reactor in circuit and go on increasing the reactance value. So you will see that when what happens when reactance is there, the power factor on load is deteriorating. Phi r is deteriorating. And because phi r is deteriorating, phi s is also deteriorating. And when phi r is deteriorating, V into I into cos phi is deteriorating. Your total power that you have to feed on the receiving end is constant. You cannot change. So power factor is constant. But the power factor is reduced. So if the power factor is reduced, voltage is constant, therefore current only has to increase. And if current increase, I square R losses will increase. And if I square R losses increase, the the efficiency of transmission line will be bad. The regulation of the transmission line will be bad. Right? That will be the effect of power factor. So that is the reason why the electricity company insists on low power factor. They say that your power factor should be as low as possible. Hmm? They are very particular about power factor. That is the reason. What is the significance of knowing the performance of line? Why should you know performance of the line? Why should you know efficiency? Why should you know regulation? Why should you know I square L losses? How can the line losses be reduced? If you want to reduce the line losses, what you can do? For reducing I square R, what you can do? For reducing I square R, what you can do? I is not within your power, but R is certainly within your power. You can reduce R. And for reduction of R, what you can do? You can increase the dimension of the wire. The diameter of the wire you can increase. But if you increase the diameter of the wire, the cost of the wire will be large. So there is going to be a point of optimization beyond which efficiency cannot be increased. I square losses cannot be decreased. Right? Because on one side you want to reduce efficiency, but for reducing efficiency you want to increase length of the dimension of the wire, but that costs. So there is going to be a uh, there is going to be between two things, there is going to be a clash. So when you want to remove clash, you have to come at optimization. So now many people in PhDs also you will see that many people are working on optimization. Optimization in terms of technology, optimization in terms of money, optimization in terms of many things, right? How can the regulation of a line be improved? How can you improve the regulation of a line? So these questions are left to you. You have to reply. Now, important part is design of the experiment. Such a small experiment also has to be designed. Many works are to be done. Before we did this experiment, before we decided that we want to do experiment, we had to do project engineering. It's a very important part. You see, 210 megawatt power plant, 660 megawatt power plant, 220 by 400 kV substation, all have to do project engineering. That is project engineering in a big way. But this small experiment also, we have to do project engineering. And if you learn this project engineering, you will be able to understand that project engineering in the field very well. That is what will happen. And that is what has happened with our student friends at BVM. They know project engineering very well. Project engineering means engineering, procurement, construction and commissioning. Right? EPCC. Engineering first you have to do, then you have to procure, then construct and commissioning. This is all to be done. For large power plants we are doing. For this small project also you have to do. So first what you have to do? You have to prepare the bill of quotation, BOQ, right? What you want to purchase, how many items you want to purchase. Then you have to prepare detailed specification according to your requirement. This is the minimum data requirement. You have to prepare the specification. And then after preparing the specification, you have to send the specification as a tender to the papers. You will not send the whole tender because tender is a very big thing. It is about 100 pages. So you will give advertisement in Times of India, in Sandesh, in Divya Bhaskar that we want to rig up a substation, we want to rig up a power plant, we want to rig up a laboratory in such and such college, and for that we want to procure things, and for procurement we want your help. So you give your quotation. So for quotation, they will have to know for what they want quotation. So a line will be written at the bottom that if you want to get details, you will have to pay a earnest money deposit of 500 rupees or 1000 rupees or 10,000 rupees. Because you see, otherwise anybody will come and take the specification. 100 पेजेस वाला स्पेसिफिकेशन सबको जानकारी मिल जाएगी. आप स्टूडेंट है, you will also go and purchase a specification. You will not have to pay anything. So they don't do like that. They ask for payment so that only genuine persons will come and they will take the details. On the basis of details, they will give the tender. Once they give the tender uh, will be evaluated technically and so there are two tenders. One is technical tenders and one is the uh, price tender. Price tender is not opened. Price tender is kept sealed. Only technical tender will be opened. They will see whether the tenderer specifies whether he agrees to all requirement of yours or not. If he does not, and it is also written that wherever you do not agree, you have to write that here you don't agree. So they are asked the question, why don't you agree? What is your objection? So to certain extent, by letters and by phone, everything will be all right. But at one point, at last point, you will have to call the tenderers, you will have to call the people, and there will be a meeting, and they will be asked to uh, give according to your requirement. They will say that if I give according to a requirement, my price will increase. You can say that yes, you can add the price and put it in the box. Then finally the prices are compared and the person who is lowest is given the order. Once the order is finalized, then the order is given to the party concerned. Once the order is given, he does not start manufacturing. He cannot start manufacturing. He has to give all drawings about equipment. Drawings means even mechanical drawings. Size. Say size of the transformer. If you say transformer height is so much and then that size of the transformer does not come to your door, आपका दरवाजा जो है उसके अंदर से नहीं आता है तो वो नहीं चलेगा. So you will have to check up the dimensions also. Mechanical dimensions, electrical dimensions, all electrical drawings, everything has to be checked up. Once you sign things, they will they will give delivery of the item, right? And once the delivery is given, the tenderer, the person is at Hyderabad, is at Mysore, person is at Delhi, person is at Ghaziabad. From there, he will send you the material to Jamnagar or Porbandar or Ahmedabad or wherever. So while transit, it is quite possible that the equipment may be damaged. Therefore, when equipment is received at the site, all commissioning tests are to be done. Commissioning test means whether any damage to the transformer is there or not. That commissioning test has to be done. Yes, you see, that is very important. So, friends, we had given this work to the, because you see, everything we cannot do. We cannot cut the panel. That has to be given to workshop. But workshop people will not do of their own. So you have to give them cut out dimensions where watt meter will be there. Watt meter outer dimension and inner dimension is different. If you give the outer dimension, then you will insert the watt meter on one side and on second side it will come out. It is of no use. So you have to give the inner dimensions of watt meter, ammeter, everything, switch, supply, and you have to prepare a drawing like this. Once you prepare a drawing like this, the workshop people will will cut the panel according to a requirement, and then they will send the panel to your laboratory. Then you have to fit everything, you have to erect everything, and once you have erected everything, then your experiment is over. Then you have to give it for experimenting to the students. It is my habit to give this sentence after talking little heavy. Drop the idea of becoming someone. You see, that is a wrong idea. I will become Prime Minister Modi. I will become Abdul Kalam. I will become Hitler, or I will become somebody. I will become uh, that uh, Bill Clinton. Hmm. Don't try to become someone, because you are already a masterpiece. Whatever God has made you is a masterpiece. Believe in yourself. Believe in what you are. What you are is best, because God has prepared you. You are not prepared. And when God has prepared, He would not prepare anything less. Bhagwan jab banayega, when God will prepare you, when God will design you, He will design in the best way. So don't think of becoming someone. You cannot be improved. Even if you try to improve yourself, you cannot improve. Whatever God has given you, that will be the fate that will happen. You cannot be improved. That means, it does not mean that if you are doing, you are becoming angry, you cannot stop becoming angry. If you are envying, you cannot stop becoming envying. All these things can be done, but as you are, if I want to become Bill Clinton, or if I want to become Bill Gates, I cannot become. That I cannot become. For that, Bill Gates is sufficient. I've got some uh, other opportunity. I've got some another way of thinking, and I will be better in my own way. So you cannot be improved. You have only to come to it, to know it, to realize it. What you can do is, what you are, you have to come to that. You have to come to what you are. You have to come what you are. You have to know what you are. And you have to realize that you are this. Once you do that much, you will be able to do wonders. You will be able to do wonders. So with that sentence, my friends, I end my speech. And when I end my speech, I always remind you, hmm, at every alternate day we are meeting, and at every alternate day we are telling that don't forget Adapt Me. Adapt Me is giving you knowledge. Adapt Me is teaching you experiments. Using Adapt Me, you will be able to design new experiments in your laboratory. Using Adapt Me, you will be able to learn much of theory, right? So using Adapt Me, you will be able to do many things. So say thank you to Adapt Me. And Adapt Me will also thank you. And Adapt Me is telling thank you, because you have patiently heard, because you have patiently understood things, because you have patiently understood the talk given by the expert. Adapt Me is bringing experts in this field, and because of that, you are getting a lot of knowledge. So, uh, Adapt Me is also thanking you, because you are trying to learn, because you are trying to get more and more knowledge. You thank Adapt Me. I I thank you. Adapt Me thanks you. I also, on my behalf, thank everybody else. So thanks. Good day. Don't forget Adapt Me. Don't forget app trace.